Thank you, Professor Donker, for your kind introduction, and welcome all to my presentation about my dissertation, which is titled Toward Interconnected DC Grids, Modeling Advanced Control Methods and a Transformer Design Framework for Multi-Active Bridge Converters. I would like to start with a brief introduction here. So here we can see the total final energy consumption of the world, first of all to the year 2024 and a forecast of it to the year 2050 from the International Energy Agency. And we can see that the energy consumption was rising in the past. However, it is forecasted to decrease. And this is mainly driven by the use of more efficient energies. So we can see the fossils are reducing here, which are shown in gray. However, this is compensated by the electricity. And up to the year 2050, we need to double our electrical infrastructure here. Thus, we cannot be wasteful with our electrical energy. We need energy efficient solutions here. And this is also highlighted by this graph, which shows the global annual investments that are necessary into our electrical power sector. This one here is forecasted to the year 2040 from the Energy Transition Commission. And they forecast that we need to multiply our annual investments by the factor of 4.2 to the year 2040 to fulfill the demands from the climate change here. This shows we do not only need energy efficient solutions, we also need cost effective solutions. So how can we achieve such a cost and energy efficient electrical infrastructure? And for that, I would like to present you today my part of the solutions. And this is based on the assumption that multi-port converters can help to satisfy the increasing demand for electricity. I would like to clarify this based on the application scenario, which you can see here on the bottom left. So there we have a residential building of the future, which may have an EV charger, a PV plant, a low voltage grid here for communication devices, and a grid connection to a public DC grid. Now we can couple all of those DC grids and DC components by conventional two-port converters, or we can use multi-port converters for that. And I assume that we reduced the costs and increased the efficiency with multi-port converters. For that, I would like to have a closer look on that, and we will give it rough numbers. So let's assume that the PV plant and the public DC grid feed 10 kilowatts of power, while the EV charger and the low voltage grid consume 10 kilowatts of power. Now, if we couple all of those grids with conventional two-port converters, we need at least 3 of them. And if we use this multi-port converter here, inherently we only need 1 device. And if we compare those solutions on a very high level, we can first of all count the galvanically isolated stages here. So these are indicated by those triangles. So we can see that we need 6 of them for the two-port converter-based solution, while we only need 4 of them for the multi-port converter solution. This shows we can reduce the component count and thus the costs here. But if we have a look on the power transfer from port 2 to port 3, for example, we can see this power is transferred to 2 of the ports, 2 of the two-port converters, thus involving also 2 times the losses. While for the multi-port converter-based solution, we have only 1 energy convergence stage in between. Thus, we can reduce the costs, reduce the losses, and increase the efficiency. In my thesis, I have answered this question here, which solution is better as an energy router, in more detail. And I would like to briefly show you the results here. So I did not only consider 1 two-port solution and 1 multi-port solution. Instead, I separated it into different system configurations for the two-port solutions and 2 different transformer designs. And I have considered 3 multi-active bridge solutions here with different transformer designs. And what these multi-port converter solutions all have in common is that they reduce the losses by 5 to 34%, and they reduce the costs by 31 to 63. This confirms that multi-port converters are the most efficient way to connect multiple DC grids. However, if we have a look in industry, multi-port converters are not yet widely used there. And in particular, my topology, which is the multi-active bridge converter. And there are 3 main challenges which hinder the widespread adoption right now. First of all, the modeling of multi-active bridge converters lacks accuracy and in particular, the modeling of multi-port transformers. And because of that, one goal of my thesis was to develop accurate but simple models, and simple means here computationally efficient. Then, with increasing number of ports for those converters, also the degrees of freedom increase. And thus, these converters bring a very high design complexity. Because of that, I wanted to lower this design burden by developing a computationally efficient framework. And the third main challenge is that there are only a few limited control strategies available. And for that, I wanted to develop efficient open-loop control strategies with fast dynamic response to enable the full potential of such a multi-active bridge. All of those goals, of course, must be validated inside a prototype converter. And for that, I needed to design and build a three-phase four-port converter here. So next, I would like to introduce you in the operating principle of such a multi-active bridge converter. Afterwards, I will talk about the design of multi-port transformers, and I will show you my newly derived open-loop control algorithms. In the end, I will finish my presentation with a conclusion and an outlook. Here you can see the equivalent circuit of such a multi-active bridge converter, here in this case with 4 ports. And we see here 4 DC grids. Each of those are connected to a DC link capacitor, shown in green, and connected to 3 half bridges, and they form one full bridge. All of the outputs of the full bridge are connected to a transformer. And in contrast to a conventional transformer, this one here has 4 leavings and 3 phases each. If we have a look on the voltages here, we can first of all see the DC link voltage, which is constant over time, which you can also see on the top right. The half bridges here are switched with 50% duty cycle. And in between the half bridges of one full bridge, there's a phase shift of 120 degrees, leading to this symmetrical 3-phase system here. If we measure now the voltages above the transformer, we obtain those 6-step voltage waveforms here. Again, there's a phase shift of 120 degrees in between. If we also consider the voltages of the other ports, we can see that they look similar, but they are scaled by their DC link voltage. And there's an additional phase shift in between, which we call load angle. And this load angle is used as degree of freedom to control the power flow within the converter. Now we have all voltages defined, but to determine the currents, it is necessary to dig deeper into the transformer here. But first of all, to keep it simple, I would like to use the single phase equivalent circuit. And for that, we place the power electronic stage by a 6-step voltage source, which you can see here in blue. And then we can have a look on the transformer. Let's start with a conventional 2-port transformer. There we can already find the equivalent circuits in the literature. So the P equivalent circuit here is obtained from the physical domain. We have 1 leakage inductance and 2 main inductances here, and an ideal transformer. And this can be mathematically transferred into the T equivalent circuit, which is well known from describing dual active bridge converters. Now, to keep it even more simple, we neglect here the main inductances as they don't contribute to the power flow within the converter. And we assume a transformer turns ratio of 1:1 so that we can also neglect the ideal transformer. If we now try to obtain the equivalent circuit for the 4-port transformer, we end up with this meshed equivalent circuit here. There we already have 6 inductances in place. And please note that I already left out all the main inductances and ideal transformers. Now, if we have a look in publications, we usually find this star equivalent circuit. However, this is not obtained from the physical domain, and it cannot be derived by mathematical equations from the meshed equivalent circuit. And this gets obvious when we count the components inside. So in the star equivalent circuit, we only have 4 inductances in place. However, in the meshed equivalent circuit, we have 6. So if we try to model our transformer with a star equivalent circuit, this lacks accuracy. And yeah, it cannot represent the transformer behavior accurately. Because of that, we are stuck with this meshed equivalent circuit. However, this brings also some drawbacks. First of all, it contains a lot of components. But if we try to extend this equivalent circuit to a further port, then we need to include further inductances, and all the remaining inductances must be reparameterized so their values get invalid. Because of that, it is not well suited to describe the electrical behavior of a multi-port transformer with an arbitrary number of ports. And for that reason, I changed to this inductance matrix here. This inherently contains also the main inductances and the transformer turns ratio. Yeah, it seems maybe to be a small step to switch from an equivalent circuit to this inductance representation here, but it lays the foundation for all the further findings in my thesis, and because of that, it's important to note. Now, if we have this single phase equivalent circuit in place with this 6-step voltage sources and the inductance matrix here, then we can calculate all the currents, which are shown in pink here, and based on that, the power flow of the converter, which is shown in green. I do not want to go too much into the math today, but I brought you the equation for the power flow of port X here, just to show you the factors of influence on the port powers. And yeah, there we have, first of all, the DC link voltage of port X here, which is represented by this variable. And we have a DC link voltage vector, which contains all the DC link voltages of the ports. Then we have the load angles in between the ports, represented by phi here. And we have the inductance matrix, which influences the port powers. There's also the switching frequency, but I consider this as a constant in my thesis. Now we have a rough understanding from the operating principle of such a converter. And with that, I would like to have a closer look on the design of multi-port transformers. What we already have seen is that the transformer parameters influence the converter behavior. Obviously, the power capability, as we have seen, but also the efficiency, as it involves losses. And it also manipulates the current waveform and thus influences the conduction and the switching losses of the other components inside the converter. So how to find the optimal transformer design for a multi-active bridge converter? And if we have a look on that, we can see we have several parameters like the core dimensions, number of turns, turn arrangements and spacing, and also further ones. And we have several targets for the converter behavior. So the power capability as seen before, but also others like the efficiency and so on. So we face this multi-objective optimization problem with several input and several output variables, and it is nonlinear and non-monotonic. I have chosen the genetic optimization here, which is inspired by the process of natural selection to solve this optimization problem. There we start with an initial population, which is a set of transformers with randomly generated properties like the core dimensions and the number of turns and so on. Then we feed them into an evaluation stage where the converter behavior for each of those transformer designs is determined. And then we select here the best behaving transformers and we combine them to create new ones. But we also use some kind of mutation to create new transformers to ensure that the optimization process here is able to break out of local minima and finds the global minimum. The steps 2 and 3 are iteratively repeated until a solution is found that satisfies the specified minimum criteria or until a fixed number of generations is reached. Then the process here is stopped. Most of those steps are already ready-made in coding languages like Python or MATLAB. However, the evaluation stage here needs special treatment for the application scenario of the transformer design. Usually, we use here finite element method simulation, as this enables us to determine the properties of transformers in several domains. So for example, the electrical domain, which we model with the inductance matrix, but also in the thermal domain and in the magnetic domain. We are able here to consider parasitic effects like the stray flux and capacitive coupling of windings, for example, and we can simulate complex geometries for the cores, which wouldn't be the case with analytical evaluations here. However, it brings one major disadvantage. It needs very high computational effort and is, because of that, time consuming. So this becomes, in particular, challenging in combination with genetic optimization, as there we have to simulate hundreds or thousands of transformer designs. Thus, the computational load can quickly become unmanageable. So how to reduce the computational effort here? And for that, I came up with this superposition of 3D FEM simulations. The idea here is, instead of simulating just one transformer design or the full transformer design here, we break it up into all the combinations of arrangements involving only 2 turns. This maybe seems to be counterintuitive because now we have to simulate several 2-turn arrangements instead of one full design, but it brings some advantages. First of all, the 2-turn arrangements have a drastically reduced mesh and thus drastically reduced simulation time. And they enable further calculations. So first of all, the interpolation. So we can interpolate arrangements just by mathematical calculations without any further simulations. And we can also calculate full transformer designs based on that. So this is a very big advantage here. So we have to simulate hundreds or thousands of full transformer designs. And now we may be able to calculate them all based on the same two-turn arrangements which we simulate. Overall, this saves a massive amount of computing time and has lower computation hardware requirements. I have used this to simulate my three-phase four-port transformer prototype here, which you can see in the middle. There, the design target was to reach the desired power levels here without any external inductors. I have used this genetic optimization approach here with a database of 5,235 two-turn simulations, which roughly took me 2 days to simulate them here on the hardware at the ISEA. And I've used this, the major constraint here was this tempo-like co-arrangement, as this leads to a symmetrical three-phase transformer. I've used ferrite material for the cores here and Litz wire for the windings. You can see the cross-section view of this transformer on the top right, and this is optimized by the genetic optimization here. If we have a look on the results, we can see that the resulting power closely meets the desired power with deviations less than 20%. And this is a very good value for transformers with integrated stray inductances, in particular for multi-port transformers with integrated stray inductances. Concluding this design of multi-port transformers, I have shown that this inductance matrix is well suited for describing the electrical behavior of multi-port transformers. And I came up with these superposition of FEM simulations to accelerate the genetic optimization here. All of those approaches are validated within a hardware prototype successfully. Next, I would like to talk about open loop control, but before I do this, I will show you my complete hardware. So I stick to this application scenario from the beginning, where we have this EV charger, this PV plant, a public DC grid, and a low voltage grid for communication devices, all coupled by this multi-active bridge converter. I just changed the power values here for more realistic values. And yeah, here you can see the complete prototype. We have this three-phase four-port transformer in place, and on top of that, the power electronic hardware stage, which you can see here. And it consists out of 4 identical power electronic building blocks that you can see here. All of those contain a full bridge of silicon carbide switches, and each power electronic building block contains a control board with an FPGA and a microcontroller. In between those power electronic building blocks, I developed a custom communication interface, as I have special demands for high bandwidth and low latency here to exchange all the sensor data and all the set values each switching period, so every 20 microseconds here. This converter is based or located here in a complete test bench setup, which you can see here. This involves also laboratory power supplies, which emulate the DC components and DC grids connected to the converter. The communication interface is very special. So here I'm using a daisy chain communication in a ring topology. The master port here initiates the communication and it sends out the data. So the set values here and placeholders for the data of the slaves. Then the slaves receive the data, modify it with their sensor data and send it to the next port. And the receiving, modifying and transmitting happens simultaneously, and thus there's only the propagation delay of the UART communication introduced. And with that approach, I can achieve the latencies of less than 150 nanoseconds. Yeah, I'm using here 3 parallel differential UART lines with low voltage differential signaling and a data weight of 40 megabaud per line. In theory, I could achieve 120 megabit per second with that. However, due to some overhead, I achieve a bit less, but more than enough for my 56 megabit, which are required to transmit 150 bytes per switching period. So every 20 microseconds. Sorry. I have also a synchronization line here for the alignment of the gate output signals. because the clock frequencies of the microcontrollers are not synchronized. Yeah, okay, now I can come to the open loop control, which consists out of steady state control, where we want to find the best switching pattern for an optimal converter behavior at a specific operating point. And it consists out of dynamic control, where we want to quickly change the operating point without inducing any additional losses. I did not focus on closed loop control, where we want to eliminate the system output error measured by a sensor. This could be a topic for further pieces here. So let's start with steady state control. Usually we model DC-DC converters in the time domain. So we separate our complete waveforms into intervals. And for each interval, there's one switching state of the converter applied. The entire waveform is then composed out of plenty of those intervals. However, for the multi-active bridge converter, this is challenging because it contains a lot of components and there's a lot of switching states. And if we want to consider multi-active bridge converters with an arbitrary number of ports, the number of switching states is not fixed anymore, and thus this approach gets virtually impossible. Because of that, I switched to this frequency domain here. We approximate the waveform, which is composed out of an infinite sum of sine waves, and this enables me to derive analytical equations which are valid for an arbitrary number of ports. However, the back transformation of those results is mathematically challenging to the time domain. There's no straightforward path to do this, but I managed it for all the important equations of the multi-active bridge converter, and this enabled me to derive two new control algorithms. First of all, the double frequency control for the single phase multi-active bridge, where we want to increase the soft switching of all the ports by introducing two additional switching events to one single port. And the duty cycle control, where we also want to improve the partial load performance, but there we use the duty cycle as degree of freedom. Due to time constraints, I will only consider this today. So yeah, the goal is here to decrease switching losses and improve the EMC behavior. So we want to achieve soft switching by manipulating the duty cycle. But what does soft and hard switching mean? So if we consider this half bridge here on the top, on the bottom left, and we consider the rising edge of the output node here, then we consider this turn on of the high side switch. And if the current is negative here at the instant of the turn on, then it was flowing through this parallel diode here at the turn on. This means the voltage is already zero at the switch. And so we call this switching event soft switched. If the current is positive in this case, then it was flowing through the low side diode, and then we call it hard switched. For the falling edge, it is exactly the other way around. So there we consider the turn on of the low side switch. And if the current is positive here, it is flowing to the diode next to the switch. Thus, the voltage is zero, and we call it soft switched. If it is negative, it was flowing through the diode of the high side switch, and we call it hard switched. If we apply this knowledge to our voltage waveforms, which are shown on the right, we can first consider the conventional control. So 50% duty cycle, which is shown in dark blue here. If we have a look on the rising edge here, so this one, then we can see that the current at the rising edge here is positive, and at the falling edge it is negative. So both events are hard switched here. However, when we manipulate the duty cycle to smaller values in this case, then we can see that we can achieve negative currents at the rising edge and positive values at the falling edge, thus soft switching. I have used this for my prototype converter and optimized the switching losses here. I would like to show you my measurements in the following. So I have measured with two control algorithms. First of all, the conventional control, single phase shift control, SPS, and the newly derived control algorithm, DCC. I have used two voltage combinations. So first of all, a voltage combination which I call symmetrical, which is shown here. So there the voltage ratio is identical to the transformer turns ratio, and an asymmetrical one which differs where the ratios differ from each other, because this is more challenging to achieve soft switching for such a converter. Because of that, I focus today on the asymmetrical voltage combinations here. And I've measured 150 operating points per algorithm and voltage combination. You can see an example here. So in the graph, I show the port powers. So power of port 2, power of port 3 and power of port 4. And the color indicates the power of port 1. And I'm also using here shadows to improve the spatial awareness here of the graph. However, the sum of all the currents must be 0 if we assume that the converter is close to lossless. Thus, we only have 3 independent quantities, and I reduce it by the power of port 1. And instead, I use the color index here to show other quantities. Here you can see the number of soft switching events per period. You see in the red area, we have 24 soft switching events, while we have 48, and thus all the switching events are soft switched in the dark green area. If we compare that to the newly derived control algorithm, we can see that there we improved the number of soft switching events for all the operating points shown here. And averaged over the whole operating area, it is increased by 35%. Thus, we are reducing switching losses and reducing the electromagnetic interference here. However, this comes at a cost. So here I'm showing the phase currents of port 4, and we can see that those currents are increased for all the operating points of the converter, and averaged over the whole operating area, it is increased by 28% for this specific port. Thus, we are increasing the conduction losses here. If we now have a look on the efficiency, we can see that the newly derived control algorithm decreases the efficiency for this specific prototype converter. And this is due to the fact that conduction losses are very dominant in this converter due to some constraints for modularity and identical power electronic building blocks for all the ports. However, if we would consider multi-port converters with a more usual loss distribution, like 50% conduction losses and 50% switching losses, then DCC would demonstrate higher efficiencies, in particular for the partial load area. I have also considered dynamic control. So first of all, why do we need it? For that, I brought you here a current waveform of phase U for a load step. And we can see before time t, we have a current waveform without any DC bias current, so it's centralized by the x-axis here. Afterwards, there's a DC bias induced, which is shown here by this gray line. And this DC bias current does not contribute to any power transfer. It only leads to additional losses of the converter. And if it's not only in the current waveform, but also in the magnetic flux, then we also risk magnetic saturation by this DC bias current. So we need to prevent these DC bias components here. In the following, I will use this alpha-beta representation here for the waveforms. There we do not only see the phase current of port U, but also the currents of the other phases. It makes use of the fact that those phase currents are not independent of one another, but their sum must be 0 according to Kirchhoff's current law. And thus, the Clark transformation here yields 2 independent currents, which are called alpha and beta current. Their DC component is visible from the deviation of the waveform center from the coordination origin. So the dashed line before the load step shows no DC bias component, but afterwards there's a DC bias component visible, also indicated by this gray cross here. If we have a look on real measurements, we can see here the switching pattern on the left. We first apply the load angle phi1 here. And at the timestamp t/2, we switch to the load angle phi2 for the second operating point. And in the current waveform, we travel first at this small hexagon here, indicated by this dashed line without any DC bias component. But with a transition, there's also a DC bias current induced. And this is dampened afterwards by resistive losses, but there are additional losses. And for the flux waveform, it behaves similarly. So there we are at first at the dashed line here. Afterwards, we travel to this continuous line where we have this DC bias component here. And this is dampened more slowly due to the larger time constant of the magnetic system here. Now I came up with 2 new dynamic control algorithms, which are extended from the 2-port dual active bridge. And there's already one in literature, which is called instantaneous current control. They all have 4 targets. They should cancel out DC currents, DC flux. They should be compatible to the conventional SPS control and compatible to the newly derived duty cycle control. The instantaneous current control, so the top line here, is not capable of canceling the DC flux, and it's not compatible to DCC. Instantaneous flux and current control here is already capable of cancel out the current, the flux, but it's not compatible to the newly derived control algorithm, and generalized instantaneous flux and current control in the end fulfills all those targets. So for the instantaneous current control, we introduce an intermediate switching pattern with an intermediate load angle. And by doing so, you can see we have closely no DC bias current here anymore. And also the flux DC component here is cancelled. However, during the transition from one waveform to the other, we can see that we exceed once the no-load hexagon here. And for larger load steps, this can also risk saturation in the transformer core, so we must prevent it. Then I came up with this instantaneous flux and current control, where we use an additional phase shift that I call here phi dash. And by doing so, we do not only cancel out the DC bias components, but we also prevent the waveform from exceeding the no-load hexagon here. For the duty cycle control in combination with these dynamic control algorithms, it gets more complicated. So there we need to classify the operating points. So the operating points with 50% duty cycle are shown here. They belong to mode C. Then we have mode A, which contains all the operating points with very small duty cycles, which lead to this triangular shaped flux waveform here. And then we have all the operating points in between, which are classified as mode B here. I came up with 4 switching switching patterns to transition in between those operating points. So today, due to time constraints, I cannot show you all of them in detail, but I will show you the properties of those, and you can have a look in my written thesis. So first of all, we have this demagnetization-magnetization transition here. This is always applicable independent of the operating points. It takes 8/3 switching periods, but we need a power flow interruption in between. If both operating points belong to mode A, then we can use the zero voltage transition, which takes a bit longer. However, there's no interruption of the power flow necessary. If one of the operating points belongs to mode C, then we can use this accelerized demagnetization and magnetization switching pattern here, which takes less than a switching period, but there's again a power flow interruption necessary. And if both operating points belong to mode C, then we can use again this instantaneous flux and current control from the slide before. This is the fastest, and it doesn't need a power flow interruption. With that, I'm at the summary of my open loop control algorithms. So I have set up this 3-phase 4-port converter prototype, which is the first of its kind. Then I have derived 2 steady-state control algorithms, and I have validated it. I have also derived 2 dynamic control algorithms and validated them. And concluding my whole thesis, I have proven that this inductance matrix here is well suited to describe the electrical behavior of multi-port transformers. I came up with these superpositions of FEM simulations, and I used it in combination with this genetic optimization approach here to reduce the design burden. I have improved the partial load performance by those newly derived control algorithms and the dynamic behavior here. And I've validated all of those approaches and control algorithms by 3-phase 4-port multi-active bridge realization here. However, all the time there's more work to do. So we could incorporate losses in the transformer model. This would be possible by switching from an inductance matrix to an impedance matrix. Then we could investigate further open loop control algorithms, for example, with other degrees of freedom, the switching frequency, for example, and we could have a look on closed loop control algorithms. And then we should also investigate fault conditions to ensure a safe and reliable operation of the converter. Yeah, with that, I'm already at the end of my presentation. I thank you for your attention, and now I'm open to questions.